at techniques for finding limits when direct substitution fails. Basically, these are the things you should try if you plug in the approaching number and you get 0 over 0. So that's indeterminate form. So these are the techniques that we should use if direct substitution yields 0 over 0. Okay, so we only have 3 listed that your book lists, and they are factor and simplify to a new function, and that one's used a lot. Rationalize the numerator, which looks really weird to students in general, but you'll get used to it. You use the conjugate and kind of clean it up and that sort of thing. And then use special trig limits to rewrite, and those will be 3 that I ask you to memorize. And there's a 4th one that's not listed up here, which I think is equally important, and that is get a least common denominator and simplify. So those are going to be the 4 things that we're going to look at today. So for our first example, we have the limit as x approaches 1 of x cubed minus 1 all over x minus 1. And the first thing you should always try is direct substitution. So if we plug 1 in, what do we get on top? 0. And if we plug 1 in, what do we get on bottom? 0. That's called indeterminate form. We're unable to determine what the limit is just by direct substitution. Usually, not always, but usually 0 over 0 is a whole, and therefore it still has a limit there. Usually. Occasionally there's a jump, so we have to be on the lookout for those. But if one of those techniques we just talked about works, and we can actually remove that whole just long enough to find the limit, then we're good. So take a look at x cubed minus 1. Can you factor that? I can. You can SOPs it. So you can take the cube root of the first, the cube root of the second, and then you can square the first. Opposite product, plus 1x, square the last. So if we factor the top, you guys good with that? Okay. So if we factor the top, notice that these guys cancel.
Okay.
What was causing the 0 over 0? That's what it was that was causing it, right? And here's a little tip, you guys. The thing causing the indeterminate form is always this variable minus this number. If you plug in and get 0 over 0, if you can figure out a way to cancel this minus this, then you can resubstitute after that and you should be able to find the limit. That indicates that it was a whole. Anytime something will cancel from the top and bottom, what makes it 0 is a whole there. But there's still a limit at a whole. So all we do now is resubstitute the 1 into the new function. So if we put 1 in now, what do we get? 3. So it looks like the limit was 3. What was going on at 1 in the original graph? There was a hole at what point? 1 comma 3. Yeah. So that was the value of the hole there. And it turns out that's the limit value as well. In case you don't remember this or you've never been shown, we'll take a second and I'll graph that for you. If you want to graph x cubed minus 1 over x minus 1, all you have to do is graph this parabola. Do you guys remember how to graph a parabola? No. No?
You make a table.
You can make a table and find the vertex. The vertex is opposite b over 2a. Yeah, so we can make a quick table over here. The opposite of b, we graph this parabola right here, is negative 1 over 2a, so negative 1/2. Someone real quick substitute that in and tell me what you get. Negative 1/2, comma what? Okay, so we got positive 0.75, and then if we substitute 1 into that parabola, we know we get 3, and negative 1 is 1, and that's enough. Let's just look at those. So that's negative 1, 1, negative 1/2, 0.75. 0 would be what? 1? Yes?
0 is 1.
0 would be 1. And then 1 would be 3. But Yes, if you look at your table, you'll see an error there. Okay, so the parabola without the hole is this graph. If I put a hole in, that's that graph. So that's what's going on graphically. So if we look as we trace in, as we approach 1 from the left and from the right, we can see that both of those are going to +3. And that's why we get the limit value when we clean that up algebraically. Any questions about this example? So let's look at the second example. We have the limit as x approaches -3 of x² + x - 6 all over x + 3. So we're trying to approach -3, right? -3.
I missed that, sorry.
If we substitute -3 in on top, we get 9 minus 3 is 6, 6 minus 6 is 0 over 0, of course. So of course I picked the one number that's going to yield indeterminate form. But the nice thing is I think we might could factor the top of that, right? So that would factor to x
Plus 3.
plus 3, x minus 2, all over x plus 3. And lo and behold, what cancels?
X plus 3.
That means there was a hole at -3. And now we can remove it by canceling, and we can look at this again and find the limit of the new function, x minus 2. So it turns out that x² + x - 6 all over x plus 3 is the exact same function as the line y = x minus 2, but the only exception is there is a hole at -3. So if I plug -3 into this line, I get -5. That's my limit. My limit is -5. That also means that there was a hole at the point -3, -5. For this example, we have the limit as x approaches 3 of x² - 4 over x plus 2. How many of you factored and simplified and got rid of the x plus 2? A bunch of you? Did you know you don't have to? Why don't we have to?
See, that's why I'm confused. Like, somehow one,
You can
direct
look at it
substitution.
and know that it's not going to do that.
Right. You would only have to do that if we were approaching -2. We're not. We're approaching 3. So if we plug in, we get 9 minus 4 over 5, which is 5 over 5, which is 1. Good news, though. If you did just get, overly excited and just went straight for factor and cancel, would you get the same thing?
Yes.
Yep. So it really doesn't matter. You would get the same thing. But you could save yourself a little bit of time and trouble by just using direct substitution to start with. Either way, you would get the same limit. Any questions about the factor and cancel technique? No?